Okay, my slides for this talk are available up on GitHub. And as a courtesy to those of you who may be less comfortable with my English, the published slides include my full speaker notes, and they will advance in lockstep with my presentation, provided that the connection here permits it. And you're going to have to forgive me for the Mozilla Chrome around the window. Apparently, we're having an issue here with the projection that seems to trigger when I put this into full screen. So I'll hope you'll bear with me on that one. So I'll give you a couple more seconds to scan this, and then I'm going to start with the talk proper.
If this is Fedora, you can just press function key 11.
I know. Thank you. Yes. Yeah. No, it is not. No, thank you. I've tried. Thanks. Yes. Okay. So welcome. This talk is about a few helpful and handy things that OpenStack can do for you, and chances are that whatever OpenStack cloud you are using or whatever OpenStack cloud you're running, it might or it will probably already be configured to do everything of what I'm about to talk about. But I've come to realize over time that a remarkable number of even relatively experienced OpenStack users just don't know about them. So I'm here to change that. My name is Florian. I'm in charge of education at City Network. And for the past 7 years or so, I've helped people deploy and operate and use and understand OpenStack. And this talk assumes, although it is listed in the beginner track, it does assume some familiarity with using OpenStack. It doesn't make any assumptions about your experience deploying OpenStack. You might find this talk useful if you've never deployed an OpenStack cloud and don't plan to. You're just an OpenStack user. But it does assume some familiarity with basic OpenStack functionality, such as how to create an instance, a VM, how to upload an image, and so on. But first off, I'm going to start with something really easy, which is, suppose you have access to a virtual machine that you know is running on OpenStack, and you might not even have created that virtual machine, that instance yourself. Someone else might have done that for you. But all that you do have is secure shell access to the machine, and you'd like to know what OpenStack platform that VM is running on. Any takers? Anyone want to offer up a suggestion on how to do that? How to find out? Sorry? Yes, exactly. I don't know if you skipped ahead in the slides, but there's actually a very simple way to do that, which is DMID code. And this command you're probably quite familiar with already. You've probably used DMID code before, say on your laptop, on a bare metal server, perhaps even your Raspberry Pi or your OpenWRT router, whatever. And DMID code really gives you a large amount of information about your system, including things like the characteristics of your CPU and RAM, how much RAM it has, etc., your network hardware, storage hardware, peripherals, that sort of thing. And at the very top of its output, it has a field that's called system information. And in a virtual machine, this information is actually populated by libvirt, in our case by Nova in conjunction with libvirt. And not only does it tell you the Nova release you're running on, which in this example is a relatively old 1706, but it also gives you some information about the OpenStack flavor that you're running on. So what your OpenStack cloud was deployed with. For example, RDO has its own product name entry, and that way you can figure out whether you're running on an RDO release. And sometimes that comes in quite handy, such as when you want to verify what your cloud service provider is telling you about what OpenStack release that they're running in a specific region. You just spin up a VM, spin up an instance in that region, and then you use DMID code to check that. So that was an easy one to start with. The second thing that I want to talk about is something that I consider a rather remarkably underutilized Nova feature, namely Nova user data. Now, you've probably seen this before. You might have used it. User data is essentially a text file that's made available to the instance, which can happen in several ways. It can be injected into the instance via magic HTTP URL, config drive, etc. And then that data is subsequently picked up by Cloud Init, and Cloud Init runs as a service in the instance's guest operating system on first boot. And we have multiple ways to specify how user data should be loaded into an instance, but the simplest one is to just pass the --user data option to OpenStack server create, which is what you can see here. You can also do that with the nova boot command. You can inject it via a OS heat cloud config resource from a heat template, etc. So multiple ways of doing that, but this is the easiest one. OpenStack server create --user data. And very frequently, this is what user data looks like. Because Cloud Init will parse any shebang, that's the hash exclamation point at the top of the user data, as a reference to an interpreter, and if that interpreter is available on the system, then it will execute this script using that interpreter. So in this case, and in this example, it's shell. The interpreter that's being used is just bin sh. But it could also be, say, a Python or a Perl script, as long as it references, say, user bin Python 3 at the top, and that executable is actually available in the guest system, it will execute that. And it's really not a good idea to do it this way, because chances are that if you're writing your user data scripts in shell, in Python, Perl, whatever, you're going to end up doing a lot of things by hand that you can really do in a much, much simpler fashion. So to illustrate what's really wrong with this, or why that's not a great idea, why using these home-rolled, handwritten scripts of any type, shell, Python, Perl, whatever, in user data, is not exactly a good idea, let me give you a quick example. Consider the following scenario. Say you want to update all of your installed packages on the first boot of a new instance, which is generally a perfectly reasonable and smart thing to do, because your image at the time that you boot the instance might be several months old, it might lack critical patches, and of course you don't want to have an insecure and unpatched system from the get-go. So upgrading all of the installed packages on first boot to the latest versions that are available from your distro vendor is generally a good idea. But if you did this with a home-rolled shell script, what you would need to do is that shell script would first need to detect what system you're running on, and then depending on that, your shell script would have to invoke, say, apt or apt-get on Debian and Ubuntu, and zypper on SLES and OpenSUSE, yum on a older Fedora or CentOS release, DNF on a newer Fedora and CentOS release, etc. So it would be quite messy, and you can do all of this much more easily. Because instead, what you ought to be using is you should just be using Cloud Config. And Cloud Config is a YAML-based format that Cloud Init will also happily parse for you and then execute what you defined in there, as it does with shell scripts, except you can now do things much more easily. Let's stick with the previous example, which is we want to update all of our packages on first system boot. Well, this is how you do that in Cloud Config. This is all that you need to put into your user data in order to get your system's installed packages to the latest that are available. So what you're writing is just 2 lines of YAML. You set 2 booleans, package update and package upgrade, both to true. And those will achieve this desired effect on any system that Cloud Init runs on, that Cloud Init supports. Meaning, at this stage now, it becomes Cloud Init's job to detect whether we're running on, say, Fedora or Ubuntu or Debian or SUSE, and will then invoke the appropriate package manager with the appropriate options and commands to refresh your package cache and install or upgrade all of the installed packages to the latest that are available, and you no longer need to take care of that yourself. It's a lot less error prone, it's a lot simpler, so you should just do it this way. There's a bunch of other things that you can also do with Cloud Config, which is, for example, you might want to define users, giving a username, group memberships, their preferred shell, as in this example. You can define sudo privileges for them, and you can even preseat their password. You can give them a password hash that you set in there so they're initialized with that password. And speaking of usernames and passwords, you might want to enable your users to actually use those to log into a virtual machine, log into an instance, which by default is only possible with a username and a SSH public private key pair, at least for Linux boxes. And suppose you want to enable username and password authentication, that's also very simply and easily done with cloud config. Again, that's just a single Boolean that you set, sshpwauth, you set that to true, and then you're no longer going to need to worry about what the SSH daemon is named on your target platform, what its configuration file is named and where that lives, what's the right syntax to reload this daemon, etc., etc. You just set a single Boolean and off you go. This is another example for a cloud config. You might want to write out arbitrary files. You can do that as well, setting, of course, the file content, but you can also, and the path, of course, because you kind of need that, but you can also set ownership, permission bits, etc., and you can do that for anything that you'd like. And you can also install packages. Again, very simple. Again, no need to worry about what our package manager is or how to properly do this. You simply provide a list variable named packages, and that list then includes everything, all the packages that you want to install. And in this example, say we want to install Ansible and Git on first boot. And then, if you really do find that there is something that you need to do that is not possible, that is not achievable with the many, many, many other cloud config features that I didn't mention here, because there's a whole boatload of them, and you do realize that I actually need to write a script of my own and then invoke that, you can totally do that as well, because for that we have the runCMD variable. So that's also a list variable, and you specify a list of commands to run at the end of the initial boot sequence. So for example, you want to run Ansible pull at the end of the boot sequence with some fancy parameters. That's totally fine. You can do that, and you can include that in runCMD in your cloud config. So bottom line, user data is something that you should totally use. It's very, very helpful and very useful, but you should use it right. You should use cloud config, make full use of cloud init's features, and just don't write your own shell scripts or Python or Perl scripts. The next thing I'd like to talk about is the importance of fast instance spin-up. Frequently, a lot of people would think that it doesn't make much of a difference if we can spin up a Nova instance in, say, 1 minute or 10 or 30 seconds or 5 minutes or whatever. And that may well be true for most use cases. But you should be aware that there are absolutely others where instance spin-up speed is a factor, which is generally true for any circumstances where you're aiming for maximum scalability and elasticity. And there is a particular storage technology that is very well suited for that purpose, which is Ceph. And the reason for that is the degree to which this is integrated into a bunch of OpenStack services. We can use one of the same Ceph storage cluster for glance image storage, Cinder volumes, Nova ephemeral storage, and also for backup and Swift compatible storage, but that's not the point of what I'm talking about here. But we have this one storage backend that we can use for a great number of services in OpenStack. And what we use here specifically is RBD, which is the Rados block device. So Rados block device means there is a device that behaves just like a regular block device, and as such it can be used by a virtualization platform like libvirt Nova. But underneath that block device does some magic that translates all block I/O into Rados object I/O in a Ceph cluster. And like many other block device types, enterprise storage or whatever, RBD is capable of creating snapshots, which are a consistent read-only view of the block device at any arbitrary point in time. And also clones. Clones are, a clone is an efficient and writable exception store to a snapshot. Or if you prefer a less jargony expression, it's a writable snapshot. And in OpenStack, we can use those pretty much all over the place. So, for example, in a situation where we do instance boot off of a Ceph-backed glance image, which means it's an RBD, and your Nova libvirt driver is also configured to use Ceph, then that means there needs to be no streaming of the image down from glance onto the compute node, the Nova compute host, which is a process that can take many minutes for large images, something like maybe 20 minutes or half an hour for images that are multiple 100 gigabytes in size. And instead, what happens when we're Ceph-backed in boot from image, what Nova does is it creates an RBD clone on your behalf, which happens in the backend, and there is no data shuffling, no streaming required, and your instance then boots in seconds, which is neat. Which is, of course, also true for boot from volume. That's essentially exactly the same process, except the clone is now being created as a persistent volume that lives in Cinder. But again, snapshot creation is practically instantaneous. Your VM boots in seconds, which is nice. Of course, you can also use the reverse approach, which is populate an image from a volume. And there, Ceph creates a snapshot of the volume, so a frozen in time view of your volume, and then populates an image with that data. And then, of course, there's also the more or less no-brainer, which is applying the RBD snapshot principle to volume snapshots. So in this case, the Cinder snapshot command that you issue via the Cinder API translates directly into an RBD snapshot, which is pretty straightforward, but it's cool because in Cinder, when it's Ceph-backed or Ceph-driven, the snapshots become really, really fast. There is, however, an important caveat that you want to take into consideration, which is all of that snapshot and cloning magic when it comes to glance images that are stored in Ceph. All of that is functional only when your RBD-backed glance image uses the raw format, which when you think about it is relatively self-explanatory. It makes a lot of sense because Ceph RBD does all sorts of cool things like thin provisioning and snapshots and resizing, etc. It does all of that natively in the back end, whereas QCOW2, our standard glance image format, does all of that within the file format. So if you store QCOW2 in RBD, you're kind of doing it all twice, which isn't very reasonable. It's not something that you should aim for. But most vendor-provided cloud images come in QCOW2 by default, right? Or maybe your cloud service provider has already uploaded an image for you. So if I have an image in QCOW2 and I really want to have it in the raw format, what do I do? That's my next thing that I'm going to talk about, which is image conversion in Glance. Suppose you have an image in Glance and it's in the wrong image format. So let's take the example. We have uploaded an image in the QCOW2 format, or someone else has done that on our behalf, but we've since realized we'd be in much better shape with the raw format, so we'd like to convert it. And normally that means you need to download the image and convert it locally with QEMU image convert and re-upload it, which is rather tedious and time-consuming, particularly when you're dealing with a large image and you sit behind a really slow internet connection, right? That becomes really boring. There is a way to do this in the Glance backend, which uses a very arcane task flow syntax, which I'm not going to show you, but I'm about to show you a way that's actually super easy, which is, we all know OpenStack volume create, right? Creates a volume. We specify the size with -- size. And now if we also pass in -- image and give an image ID, we initialize the volume with the contents of that referred image. And importantly, what happens is the glance image automatically gets converted to the raw format as it's being translated into a volume. You can also do the reverse, which is OpenStack image create with -- volume, which means that we tell Glance to create a new image, which is, however, populated with the volume's content. And now that image always retains the format of the source volume. So if the source volume is raw, then we also get a raw image. So that means if we take an existing image that is, say, QCOW, convert it into a volume, and then convert the volume back to an image, we have just converted a Glance image from QCOW to raw using just OpenStack backends, which is nice, right? Because it's relatively quick and easy to do this, and it doesn't require rather tedious downloading and uploading, right? Which might come in handy. My next topic are availability zones. Now, availability zones in OpenStack, we've had those for a while, and they have something of a reputation of being somewhat mysterious and difficult to use, which really is rather undeserved at this point. You should totally be aware of how they work, but it's not too complicated or counterintuitive, and you should be aware of what they can be used for. Now, as a very quick recap, what are availability zones? Availability zones are something that divides your compute environment or your public cloud provider's compute environment into failure domains. So by operating availability zones, a cloud provider makes the following statement or the following guarantee, which is if you're running resources in one availability zone, and there is an outage affecting that availability zone, then resources that you choose to run in other availability zones will be unaffected by that same outage. Okay? Now hang on, there is a slide missing for some reason. Okay, sorry, that didn't render correctly for whatever reason, but I'll give you the rundown anyway. So suppose we've got two availability zones, right? Like for the sake of argument, let's name them left and right. Okay, so this is the left availability zone, this is the right availability zone. So what I can expect is that if one of the availability zones fails, so say the left availability zone fails, then resources in the other availability zone will be unaffected by that same problem. Okay, so if this availability zone over here goes down completely, then the resources here should not be affected by that same thing. Okay, so what are availability zones not, right? Availability zones are not host aggregates. Host aggregates are for grouping your compute nodes by specific characteristics. So for example, some of your compute nodes might have specific, like they might have like specific GPUs, or they might have access to an InfiniBand fabric or something like that, right? Some do, some don't. And those properties can of course overlap, because a compute node might have access to an InfiniBand fabric and a specific set of GPUs, and this set over here only has access to the fabric and so on, right? So any compute node can always be in 0 or more host aggregates, but it can only ever be in one availability zone, right? AZs are also not cells. Cells are for hierarchical scheduling in OpenStack environments with very large numbers of compute nodes. And so basically hierarchical placement. And availability zones are completely orthogonal to cells. So that means you can use them both, but you can also not use cells at all and just have availability zones. But they're definitely not the same thing. And then finally, availability zones are also not regions, because regions are separate OpenStack clouds in their own right, which are normally just unified by a single service catalog and a unified user authentication scheme and possibly a global image store, right? Where you have like the same images available from all regions. And as such, regions really transcend the scope of availability zones, and also cells and host aggregates. All of those are just compute only. And a region really has its own controllers and everything, right? They're literally like separate OpenStack clouds that are just unified by some common configuration. So any region can always contain one or more availability zones. Any availability zone can only ever be in a single region, but again, they're definitely not the same thing. What OpenStack services support availability zones? Availability zones are supported by Nova through Nova Compute, by Cinder through Cinder Volume, by Neutron through the gateway node agents. And there are other sort of more high-level services that also support availability zones, but for the moment I'm going to talk about these three. There's one thing that you should know here, which is there is a small but relatively important difference between Nova and Cinder on one hand and Neutron on the other, which is that in Nova and Cinder you get exactly one AZ that you can set when you're creating an instance or a volume. And if we can't create the resource in that availability zone, then that becomes a scheduling failure, right? It's just your resource just fails to launch. But in Neutron, we can actually define a list of availability zones, and if one availability zone is not available for whatever it is you're creating, say a router, then it will try the next and so forth, which is a small difference. There's a neat feature about availability zones, which is that in many cases you have to specify the availability zone on one resource only, and then other dependent resources will follow suit. So for example, you can create an instance in a Nova availability zone, and you configure that instance to do boot from volume, where the volume is being created on the fly from an image. Right? So for those of you using Horizon, for example, that's something you can set in Horizon. You can say boot from image, and then you select an image, and then there's a little toggle that says create volume, and then you can create a volume. And if you do that, in this case, and you specify an availability zone on the VM, on the instance only, then the Cinder volume that's being automatically created on your behalf will be created in the correct availability zone. In other words, the one that matches the instance, which is nice. Which comes in very handy in combination with the next feature I'm going to talk about, which is the Cinder image volume cache, which is a feature that's a little bit obscure because it's especially useful in a very specific scenario. So consider Nova and Cinder do support availability zones. They play rather nicely with one another, and you could have multiple physical locations. And again, there's a slide missing. I apologize for that. But I'm going to explain the picture to you anyway. So suppose, again, I'm going to use left, center, and right here. Okay? Suppose we have a single OpenStack region, and we have 3 data centers representing 3 availability zones. In the AZ center, that would be me. That's the one that has the compute infrastructure plus control nodes, right? So that's basically sort of the center of the region. And then we have an AZ left and an AZ right, and both of those just have compute infrastructure, right? And what's more, let's further assume that every availability zone uses a different storage backend. So say here in the center we have Ceph, and over here on the left we've got EMC, and over here on the right we have NetApp, say. And there's one thing in this scenario that doesn't know about availability zones, which is Glance, right? So Glance still doesn't know about availability zones. And conventionally, therefore, if we fire an instance up in one of the remote locations, left, right, it will do one of 2 things, which is either it would have to stream the image down to the compute node once for each compute node. So if I fire up something here on the left, then we'd have to like shuffle a bunch of data over there to fire it up, which is a pretty bad waste of bandwidth, and it also means really slow instance spin up, so not good. Or it would assume that it has permanent access to the original image and then create a shallow copy on write a clone from it, which is what happens if your Glance backend and your Nova RBD uses, Ceph RBD. So that's easy on bandwidth, but that's terrible in terms of latency because every time the machine over here needs to access something that lives in the original image clone, it has to like talk to the central location, and that's terrible. Okay, so what can we do? We can enable a neat little feature in Cinder that's called the Cinder image volume cache. And when it's on, every time an image is used for the first time, it is streamed down to the Cinder backend, and a copy is created there. And each subsequent use of that image then doesn't need to be fetched from the primary Glance location, but it can simply be served from the local image cache. And we can also limit the maximum size of an image that needs to be cached in the local Cinder store. That's the maximum size per image, not the total size. And we can also limit the maximum number of images that can be cached at any given time, which is really helpful, and it's a really neat feature if you're running that sort of setup where you have multiple availability zones that are sort of dispersed geographically a little bit. Can come in really, really handy. Another thing that can come in really handy, but I think is really underutilized in OpenStack Nova in this case, is the ability to suspend and resume instances, so virtual machines, and even arbitrarily complex distributed environments. I think this is a very, very useful OpenStack feature, but it's rather important to understand what those actions do. So most people would think that if you do OpenStack server suspend, what would happen is that your process, your KVM process, would just get a stop signal from the hypervisor, and the corresponding resume command would send cont, right? Stop sig cont. And you'd be forgiven to think that because that's exactly what virtualization does in libvirt. But that is not what an OpenStack server suspend does. Instead, what OpenStack server suspend does in libvirt is called a managed save operation, which is that the content of the virtual machine's memory is written to a file, which is called a save file, and then the KVM instance is shut down completely, and when it starts back up, it detects, okay, here's a save file, it comes up, it pauses, reads back the memory from the save file, and then unpauses, and then the machine continues to run. But what's neat about this is that because your image, while it's being suspended, that is managed saved, is effectively shut off. It consumes during that time 0 RAM and 0 CPU, and RAM hours and CPU hours are the most expensive thing that you pay for for a public cloud VM. So that means that while an instance is suspended, it will rack up almost no cost, which is really neat. I say almost because there are things that your cloud service provider will still bill you for, like allocated storage or allocated publicly routable IP addresses, because those don't magically just go away and they can't be reclaimed, but that's going to amount to a very tiny fraction of the cost of a VM running throughout. So that's very helpful. OpenStack Server Suspend is great for test environments, which means, you spin something up, you test something, you suspend it, you come back 2 weeks later, and it didn't cost you anything in the interim. But what's even more useful is OpenStack Stack Suspend, because you can do this with a whole heat stack, even if it has nested resources. So even if you use, say, resource groups or things like that, that will work as well. It will suspend all the VMs running in that stack. When you do that, my next thing comes in particularly handy, which is the QEMU guest agent, which is a way for libvirt or QEMU KVM to communicate with a guest. And to do that, for you to be able to use that, you have to fulfill 2 prerequisites. First, you need to set a property on an image. HWQEMU guest agent needs to be set to yes. When you do that and you fire up a new instance, libvirt will configure it to include a virtual serial port that can then be used to communicate with QEMU guest agent in the instance. And then, of course, you also need QEMU guest agent in the instance, which by now you've already learned you should be deploying with cloud config and a packages list. So if you do that and you spin up the instance, it will just install QEMU guest agent right on first boot. And then, for example, when Nova wakes up one of your VMs from suspend, it will use its virtual serial port to set the guest set time command via QEMU guest agent via the serial port to QEMU guest agent running in the VM, and therefore your machine then immediately has the correct time when it wakes up. Some instances don't care about wall clock time, many do, so this can be very helpful. The guest agent also does another thing, which is that if you take a snapshot of an instance, it will freeze the file systems. It uses the fsfreeze IO control to freeze file systems so you have a clean snapshot, which is also nice. Speaking of snapshots, that is also something that you can do with an entire stack. That's pretty cool. Stack snapshot and a rollback. You can do OpenStack stack snapshot create, which takes a snapshot of all of the persistent things that are in the stack. So that is to say, creates a snapshot of every VM. And you might think it also creates a snapshot of every Cinder volume, which is not quite what it does. Which is not quite what it does. So if you do a stack snapshot for all of the VMs that you have running in there, it does indeed create a snapshot. So you get images ending up in glance to do that. But what Heat Engine really does when you take a snapshot of a stack that has volumes, it doesn't create volume snapshots. Instead, it creates volume backups via the Cinder backup service, which also means, by the way, that if your cloud doesn't run Cinder backup, then you don't get heat stack snapshots, at least not for stacks with volumes. And the thinking behind this is, of course, that if you were to ever delete a stack and also have the stack configured to delete its volumes in the process, then when you delete a volume, the volume snapshots go away as well. And presumably that's not what you want. Instead, you want your volume contents to be preserved for posterity in some way, and backups do that for you. So the stack snapshot also actually translates into a Cinder volume backup. Okay, and my final thing, nested virtualization, which is an interesting OpenStack feature. Again, many people don't need that, but if you do, it comes in very, very handy. What is nested virtualization? Nested virtualization is running KVM in KVM. That is to say, you run KVM with hardware acceleration within your Nova instances that are themselves running in KVM. And in KVM parlance, we call this nested guests. Now, this has a few interesting limitations that are inherent to KVM. They have nothing to do with OpenStack. So for example, when a Nova instance runs nested guests, while it's running them, you can't suspend it. That is to say, you can't actually suspend it, but it'll kernel panic on resume. That's just what it does. And because suspend, or rather managed save, is actually really the same thing as live migration writes the same content to a TCP socket that managed save writes to a file. The same thing also applies, the same consideration applies also for live migration. So if you have a VM that's running nested VMs, it won't be able to live migrate while it's running them. Again, it will actually succeed in the live migration, or look like it does, but then it will kernel panic when it unpauses from the migration. And there's and this is what I'm going to close out on, there's an interesting consideration here. This is primarily for those of you operating OpenStack clouds. You know, this is the default configuration for libvirt, CPU mode host model. That means the VM basically copies the feature flags of the CPU, and that sometimes creates issues with live migration. If you live migrate it from a host, I see people heavily nodding in the room that have run into this apparently. You live migrate from a host with a newer CPU to one with an older CPU, and the older CPU doesn't have the feature flags, and so then the live migration fails. So frequently operators do this, right? They set CPU mode equals custom, and then they define a CPU model that matches the oldest CPU on a hypervisor in their inventory. And when you do that, you might be in for a rude surprise that has to do with the meltdown attack. Or rather the many mitigation patches to the Linux kernel that have been rolled out for the meltdown attack, many of which have a very significant performance impact on virtualization workloads, except if the VM also has access to the process context ID or PCID CPU flag. And guess what? Some popular CPU model options, such as the aforementioned Ivy Bridge, do not pass this flag in by default, right? So that means that you now need to overwrite this in your Nova configuration so that you do get this flag passed in. You do it like this with CPU model extra flags. But there's a limitation in here, which is that in OpenStack releases up to and including Queens, the VMX flag, that's the one that enables nested virtualization. That's why I'm mentioning this in this section. The VMX flag is not a supported CPU model extra flags option. And that means if you're running an OpenStack release before Rocky, you cannot do nested virtualization and also have this PCID optimization in there. But since Rocky, that is now supported, and you can totally do both nested virtualization and get the PCID flag. You just set an old CPU model, and then you set CPU model extra flags, PCID, VMX, and you're good to go. And there's a bunch of other CPU model extra flags that you might also want to set, which is all nice. Okay, so that's my list of 10 things you may not have known what you could do in OpenStack. Now you know. And my slides for this are, again, up on GitHub. They are under a Creative Commons Attribution Share Alike license, so if you want to reuse this talk, you're very welcome to. And I thank you very much for your time. I'm going to stick around for questions if anyone has any. Enjoy your lunch. Thank you.